So let's look at how we might calculate sy.x. And I don't know if you remember Shrek. I think everybody's seen Shrek. Hopefully you have. There is a scene where he goes, "Hold the phone." And this kind of reminds me of that sort of situation. We need to hold the phone. Something's wrong here. Something's not right. All right, so let's look at how we would calculate the average distance y is to y prime. Well, we can just figure that out and say, well, what do we have to do to find an average distance? We did that when we first learned about variable x and we wanted to calculate variance and standard deviation. Remember, we needed to figure out, well, how far is each x from x bar? Well, it's the same thing here, only now we're trying to figure out how far each y is to y prime. So we're not using how far each x is to x bar. We're looking at the difference, the distance, which is also a difference, but we're looking at the distance between each y and y prime, okay? So we're going to need to figure out what this distance equals, and this one, and this one, and this one, and this one, and this one. So we're going to get all of our y minus y primes. Okay, that's all the distances, but now we want the average. So what do? We have to add up all of our distances and divide by however many distances we have. So in this case, we have, well, how many points? We have 6, right? So we would divide by 6, but just like when we were figuring out standard deviation, remember there was an n minus 1 in the formula? Same thing for variance, there was an n minus 1. Now the correction is n minus 2, all right? It's just a correction. Otherwise, our statistic would be biased. Remember that? All right? So we're going to apply this correction n minus 2. So again, we take all of the distances, add them up, divide by n minus 2. There is a problem. Can you think about what the problem is? I shouldn't have shown you that, right? If you do all these, shouldn't have shown you this, that is. If you do all these y minus y primes here, this y value is going to be larger than this y prime. This one is going to be also larger, a bigger number than this y prime. And same thing here. So all of these distances are going to be positive. And then all of these distances are going to be negative because this y is smaller than this y prime. So when we do y minus y prime, we're going to get a negative answer. So here we have positive differences. Here we have negative differences. This line here is balancing out all the data points, right? That's how the regression line is drawn. It's to minimize the average distance. So it's kind of like a balancing point. It's reached that point when it's minimized the distances. So knowing that it's balanced out these distances, if you just try and add them all up, all the positive and the negatives, what are you going to get? Oh, I shouldn't be here. Not yet. Anyways, you should be thinking, oh, this sounds like deja vu. What does it mean? You've seen this before. You're going to get 0, right? The positive distances are going to cancel out the negative distances. All right? We saw this happen when we learned about variance, when we first learned about variance and standard deviation. Remember we said, before we even learned about those, we said, let's just calculate the average distance that x is to x bar. And when we did that, half of the x minus x bars were negative, and the other half, the x minus x bars, were positive. And when you added them all up, you got a big fat 0. Well, the same thing is going to happen with the y minus y primes. Half of them are, those distances are going to be above the line and half below the line. When you add them all up, you're going to get 0. Well, how did we solve the problem initially when we were looking at the average distance x is to x bar? Well, we squared all the distances, right? Do you remember doing that? We just said, oh, yeah, all you have to do is do x minus x bar squared. Then find the next distance, x minus x bar, and then square that. And square all your distances. You'd have to do that first, and then you find the average squared distance scores are to the mean. What was that called? That was called variance, remember? The average squared distance, x is to x bar, or x is to mu, right? The average distance scores are to the mean, squared distance, the average squared distance scores are to the mean is variance. But we decided we didn't like that. We didn't like working with squared numbers. So how did we get standard deviation? We just took the square root, right? So this should have popped up later. But we just take the square root, and then we get units back to the original form. So we're going to do the same thing to find Sy.x, all right, standard error of estimation. What we're going to do is we're going to get all the y minus y primes. We're going to get all those distances. But before we add them up, and that's key, you have to do this before you add them all up, you're going to square each distance. So you're going to get y minus y prime squared for the first dot. Then you're going to go to the next dot and you do y minus y prime, all right? And you square that one. And then et cetera, until you've gone through all your dots, all right? Now, after each distance is squared, then you add them up. And there's no way this can come to 0. Well, I suppose if all your y's were on your y primes, then yes, there would be no distances. If all the points fell on the line, there's no distances, and so this would be 0. All right? But there's no way it could be negative because you're squaring, and a squared number can never be negative. So once you have all these squared distances added up, divide by n minus 2. What would that give you? It would give you the average squared distance that scores are to the line. And this would be s squared y dot x, right? S squared y dot x. But we don't like dealing with squared numbers. How do we get rid of that? We take the square root, okay? And then once you take the square root, this goes from s squared y dot x to just s y dot x. So it's exactly the same thing as when we went from variance to standard deviation. Variance was an average squared distance. To get an average distance, we just took the square root of variance. Okay? So Sy dot x is basically a standard deviation. But it's not a standard deviation for a data set. It is the standard deviation for the scatter plot. All right? So now we can say that the regression line is to the scatter plot as the mean is the center of gravity to a set of scores. I know, a lot of people hate these analogies, but I want you to see the similarity, right? The regression line is trying to find the sweet spot, if you want to look at it that way, much like x bar is, or mu, right? X bar and mu are trying to find the sweet spot for a set of scores. It's trying to find the center of gravity. Well, the regression line is trying to find the sweet spot for the dots on a scatter plot. It's like it's trying to find the center of gravity for all the dots, all right? But we don't generally call it the center of gravity for all the dots. We say it is minimizing the average distance, vertical distance scores are to the line, right? The y values are to the line. And just like S, if you were to calculate standard deviation for a set of x's, so for a data set, standard deviation is the average distance points are to x bar, let me say that again. S for a set of x's, standard deviation for a set of x's, is the average distance x is to x bar, or x is to mu. Sy dot x is the standard deviation for a scatter plot. So this time, it's the average distance y is to y prime. But the concept is the same. They're both measures of standard deviation. Either you're looking at the spread of x values, right? In the case of standard deviation for x, you're looking at dispersion of x values, whereas Sy dot x is looking at the dispersion of dots on a scatter plot. If there's no dispersion, it means all those dots are on the line, and Sy dot x will be 0. But if those dots are moving away from the line, Sy dot x is going to be bigger, right? It's measuring dispersion. It's going to increase. And if, when would we see the most amount of dispersion? When we have no relationship between x and y. So in other words, if r is 0, no relationship between x and y, that's when we're going to see Sy dot x, this measure of dispersion, this measure of the average amount of scatter or error, that's when it's going to be highest.